Hello, sir. My name is Nur Ali Nabiha. Today, I will be presenting the enhancement made to our linear regression lab. Since okay, I will directly walk through the code and its output in the notebook. Okay, my goal with this enhancement is to improve clarity, introduce advancement concept, provide better visualization, and apply the methods to real-world data. So by doing so, I aim to deepen our understanding of linear regression and its practical application. So we move to the first enhancement, which is understanding simple versus multiple regression. First, we look at the difference between the simple regression and multiple regression. Simple regression use a single independent variable to predict the dependent variable, while multiple regression uses multiple independent variable. In the notebook, we generate a dummy dataset with 3 features and a target variable. We then split the data into training and testing set. After fitting the simple and multiple regression model, we calculate the R-squared, MSE, and RMSE to measure the model performance. The printed output in the notebook shows that the simple regression R-squared 0.988 and multiple regression R-squared 0.93993. So this high R-squared value indicate that both models fit the data well, with multiple regression performing slightly better. And then we move to the second enhancement, regulation technique, Ridge and lasso regression. So to improve our model, we introduce Ridge and lasso regression to handle multicollinearity and prevent overfitting. This model modify the standard linear regression by adding a penalty to the model coefficient. So after running the Ridge and lasso model, we compare the R-squared score, MSE and RMSE. With this result, that Ridge and lasso provide similar performance but can help improve generalization in more complex data sets. Okay, next, the third enhancement, which is visualization feature relationship and residual. To better understand our data set, we visualization it. First, we use correlation heat map. So this show the relationship between features and helping us detect multicollinearity. And then residual plot. This helps us to check if the model assumption hold, such as constant variance and normality of residuals. So in this notebook, the correlation heat map reveals strong correlation among some features, while the residual plot helps us validate the quality of our regression model. And then comparing scikit-learn and step model, we compare two different implementation of linear regression. Scikit-learn, which provide a simple and efficient implementation, and then step model offer the detailed statistical summary, including p-value and confidence interval. So the output in the notebook include this and this. So both model give similar result, but step model provide a more detailed statistical analysis, making it useful for deeper interpretation. Next, okay, applying regression to a real-world data set. So to apply our learning, we use a real data set. which is the fish market dataset, which contains weight and physical measurements of different fish species. So after running our regression model on this dataset, the result shows okay, this R squared, simple regression using simple regression R squared 0.81 and multiple regression R squared 0.88. So this confirmed that our model performed on a real world structured data with multiple regression capturing more variance. And then evaluating Rich and Lasso on real data. Where is it? Oh, this one. Okay. So as you can see, the result confirmed that adding regularization technique does not significantly improve performance in this case, but they help prevent overfitting in complex scenarios. Okay, so to conclude this lab, in a summary, this enhancement make the linear regression lab more informative and practical. So we explore the difference between simple and multiple regression, the benefits of regularization techniques, visualization to understand data relationship, a comparison scikit and step model, and application to a real world data set. So through this improvement, we now have a better understanding of linear regression and its application. Thank you and
Good afternoon to Dr. Wong Yaping. So my part is logistic regression lab enhancement. Okay, for this lab enhancement, focuses on improving the understanding and application of logistic regression with Lasso and Rich regulation using a real-world dataset, which is the PIMA Indians dataset. The PIMA Indians diabetes dataset. The objective was to explore more advanced concepts related to regularized regression models and demonstrate how they can be applied to practical problems. Okay, first, this is the code for the import necessary libraries. Then for the logistic regression overview, logistic regression is a statistical method used for binary classification problems. It predicts the probability that a given input belongs to a particular class, unlike linear regression, which predict continuous values. Logistic regression output a probability value between 0 and 1 using the sigmoid function. The model applies a decision boundary, typical 0.5, to assign class labels. This is the logistic regression equation. Logistic regression is often used in fields like healthcare, finance, and marketing for tasks such as predicting whether a patient has a disease or whether a customer will buy a product. This is the key concept in logistic regression. First, we have the sigmoid function. It transforms linear prediction into probabilities range 0 to 1. This is the formula. It used to classify data point into binary categories. Second, we have the decision boundary, the threshold at which probabilities are divided into classes. The default threshold is 0.5. This is the advanced concept that I will apply, which is the regulation in logistic regression. Regularization is a technique used to prevent overfitting in models, particularly when dealing with a high-dimensional data. For logistic regression, two common types of regularization are lasso regularization, which is L1, at a penalty equal to the absolute value of the magnitude of the coefficient. It can drive some coefficient to 0, effectively performing feature selection. Rich regularization, which is L2, adds a penalty equal to the square of the magnitude of the coefficient. This technique helps to shrink the coefficient but does not eliminate them. This is where I load and explore the dataset. I'll be using the PIMA Indians diabetes dataset, which have a few attributes which contain pregnant, glucose, BP, skin, insulin, BMI, pedigree, age, and label. This is where I display the dataset information. And this is where I check the missing values. So there's no missing value in this dataset. This is for the data visualization. This is where I explore all the attribute using the box plot. This is the box plot for pregnant, for glucose. This is for BP. And this is for skin. And this is for insulin and BMI and also pedigree. This is the box plot for age and label. For the data processing step, I divide the data into features and target. And my target is label. Here I visualize the correlation heat map to understand the relationship. This is the correlation heat map. Then I started with train and test split dataset. Then after that, I started with the model training for logistic regression. This is where I develop and train the models. And this is the accuracy of the logistic regression, which is 0.71 accuracy. Then for the L2 and L1, I search for the best C with hyperparameter tuning, and it's generated that best C for reach is 10 and best C for lasso is also 10. So I've started with the application of logistic regression with lasso and reach models. This is where I apply the reach regularization. This is where the lasso regularization. Then this is the model evaluation. This is where I evaluate the models. Here, as you can see that the logistic regression with rich models give the accuracy of 0.72, and logistic regression with lasso model give 0.71 accuracy. This is where I cross-validate the result. The result generate the same accuracy for both logistic regression with L1 and also L2. Then I also compare the logistic regression with reach, logistic regression with lasso, with decision tree, and also support vector machine. This is where I develop the models and train and also evaluate it. For the logistic regression, it gave the 0.71 accuracy, and this is the confusion metric of the logistic regression, and this is for logistic regression with rich model and which give the 0.73 accuracy, and this is the confusion metric. This one is the logistic regression with lasso, which give the accuracy of 0.71, and this is the confusion metric of it. Next, for the decision tree, it gives the accuracy of 0.71. This is the official metric, and also SVM, which gives the accuracy of 0.72, and this is the confusion metric. So then I code for the comparison in a box plot in a histogram type. So here, as you can see that logistic regression ridge is better than other models. Then I also visualize it with ROC curve analysis. This is the ROC curve comparison between between all the models. For the discussion part, advantages and disadvantages of logistic regression. The advantages is logistic regression is simple and efficient for binary classification. It provides probabilities for prediction and easy to implement and interpret. While the disadvantages is assume linearity between features and output, sensitive to outliers, may not perform well on complex data set. This is the advantages and disadvantages between the three models. Logistic regression perform well in linear data, interpretable, but sensitive to outliers, while decision tree capture complex relationship but prone to overfitting. And support vector machine is effective in high-dimensional spaces but computationally expensive. That's all for my lab enhancement. Thank you.
Good evening, my name is Nabila and today I'll be presenting my enhancements to the Gradient Descent Part B lab exercise. So the purpose of these enhancements was to deepen our understanding of gradient descent by visualizing its behavior, improving its performance and applying it to real-world datasets. I have implemented 5 key elements that clarify learning rate selection, introduce modern optimizers, visualize decision boundaries, and evaluate model performance. So first up, I implemented gradient descent with 3 different learning rates, 0.01, 0.1, and 0.5. Then I plotted the cost function over 100 iterations to see how the learning rate affects convergence. And as we can see from the chart, with a small learning rate, the blue line, convergence is very slow. The moderate learning rate, the orange line, balances speed and stability, while the higher learning rate, the green line, converges quickly. However, if the learning rate were too high, the model could diverge instead of converging. Next, I implemented both standard gradient descent and the Adam optimizer and compared their loss curves over multiple epochs to see which one converges faster. So from there, we found that the Adam optimizer, the orange line, converges much faster than the standard gradient descent, the blue line. And this happens because Adam dynamically adjusts learning rates per parameter, preventing slow learning or oscillations. Eventually, I plotted the decision boundary of the trained logistic regression model to see how it separates classes. But, however, the decision boundary appears unexpectedly vertical, as you can see from the plot, and this suggests that the model might be relying only on one feature. So this could indicate a feature scaling issue or dataset bias. So eventually I applied gradient descent based logistic regression to the breast cancer dataset and evaluated its performance using accuracy, precision, recall, and F1 score. And from there, we found that the model achieved 97.3% accuracy with high precision and recall for detecting cancer cases. And this confirms that gradient descent, when properly tuned, is effective for real-world classification problems. And lastly, I plotted the ROC curve and calculated the AUC score to better evaluate the model's performance. So as you can see from the plot, with an AUC of 1, the model classifies perfectly. However, if this score was obtained on training data, it could indicate overfitting, and the ROC curve provides a better evaluation than accuracy alone, as it considers both false positives and false negatives. So through these enhancements, it helped us better understand how gradient descent works in different conditions, how optimizers like Adam improve upon it, and how we can evaluate model performance beyond basic accuracy. More importantly, these enhancements showed that gradient descent is not just a theoretical concept, it's a fundamental optimization method used in machine learning today. Thank you.
Hello, my name is Michal, and I prepared to demonstrate our lab enhancement for k-means clustering. So for the beginning, I would like to explain what is k-means clustering, and then I will proceed to our enhancement. So k-means clustering is an unsupervised machine learning algorithm used for clustering data into groups based on similarity. Basically, how it works, we have to choose k number, which is number of clusters. The user specifies how many clusters they want to create. Then we have to initialize centroids, which is randomly selected k points from the dataset as the initial cluster centroids. Then assign points to the nearest cluster. Basically, each data point is assigned to the cluster whose centroid is closest. Then update cluster centroids, which recalculates the centroid of each cluster as the mean of all points assigned to the cluster, and we have to repeat until convergence. For this demonstration, I've prepared some dataset. Basically, if I run this code, this make blobs method basically generates like our data. There are 300 points in the image. For centers, cluster STD is standard deviation of each cluster, and random state 42 is a seed for a random number generator to ensure reproducibility. So basically, this is how k-means clustering works, and to simplify things, we have to imagine it as if we have a data set, for example, with customers which like spend their monies. So k-means clustering could group customers into, for example, high spenders or medium spenders or low spenders, or non-spenders in this case. So basically, this is how k-means clustering works and how it is used, and or what it is used for. Okay, let's now proceed with key enhancements, which are basically detailed explanation of k-means clustering, which I already did. Then advanced initialization techniques, for example, k-means plus, visualization, for example, elbow method, application of k-means on a real-world dataset, and comparison with the clustering methods, with discussion on advantages and limitations of k-means. So let's proceed with the elbow method. The elbow method is a technique used in k-means clustering to determine the optimal number of clusters by analyzing how the sum of the squared errors changes as k increases. Basically, we have to train multiple k-means models with different values. For example, like with 1 to 7, then calculate the sum of square errors, which is SSE, for each value of k. SSE is the sum of square distances between each data point and its assigned cluster centroid. Plot k versus SSE on a graph. Basically, when I run this code, we identify the elbow point. The point where the SSE curve bends is considered the optimal key point, which now is 3. And after this point, adding more cluster doesn't significantly reduce the SSE. So basically, that's the elbow method. Okay, and the last point is real-world application of k-means clustering, for example. So I imported IRIS dataset, which is basically famous dataset for flowers. It contains 150 samples of 3 iris species based on 4 features, and the dataset is clustered into 3 groups because I selected 3 clusters. Without using actual labels, relies solely on feature similarities. A scatter plot visualizes the result with the points color-coded by clusters and X marked indicating cluster centroids. Basically, we have 3 by the clusters generally aligned with the species. Some overlap can occur, especially between versicolor and virginica due to their similarities. So that's our real world. Basically, how can we use k-means clustering in the real world problem? And the last point I would like to talk about is advantages and disadvantages of k-means clustering. For advantages, they are simple and efficient. They are fast convergence. That means the algorithm quickly finds cluster centroids, and they are versatile, which is like they're widely used in various applications, for example, like customer segmentation and anomaly detection. And disadvantages, they required a predefined number of clusters. They are sensitive to outliers, and there fails to non-convex shapes. So that's all for k-means clustering. So thank you.
Good evening, my name is Nabila and today we'll be presenting our project for machine learning. So first of all, what we did was data pre-processing, where we cleaned the data. We started with a dataset containing rental listings in Klang Valley, and key features included monthly rent, the number of rooms, bathrooms, parking availability, facilities, and additional amenities. Our first step was to clean and pre-process the data to ensure consistency and usability. So some of the processes in cleaning that we did was handling the missing values. Rows missing critical attributes like rooms and bathrooms were dropped, and missing parking values were assumed to mean no parking and set to 0, and missing facilities were filled using an aggregated approach per the property name. So basically what we did was we looked at a property name. In the non-null values for its facilities, we aggregated them together and we made it uniform for all the property names, for all the facilities in the said property name. And other than that, for the monthly rent column, Initially, it contained strings with currency symbols and text. So we removed all those unnecessary strings like RM and per month, and we converted them into numerical format for easier use later on. So eventually we did outlayer detection and removal. So what we did was, to prevent extreme values from skewing our predictions, we used the interquartile range method to remove significant outliers in monthly rent. Any rental values outside 1.5 times the IQR were considered extreme and removed from the dataset. And moving on. So once cleaned, we explored the dataset to understand trends and relationships. And the insights that were gained in EDA were later on used for feature engineering and PCA.
Hello, sir. My name is Nooralina Nabiha. Okay, today I will walk you through the feature engineering steps that applied to our data set. So firstly, we ensure that the monthly rent column is converted to a string type before performing text operation. We then clean the values by removing unnecessary text like R per month before converting them back to float for numerical analysis. Next, we standardize the size column by converting it to a string and extracting the numerical square feet values while removing any additional text or comma. And for categorical features, we use label encoding to transform the location, property, and furnish and region columns into numerical representations, which are essential for machine learning models. And then we introduce a new feature, which is price per square feet, which help in understanding rental pricing relative to property size. And then we finally handle the missing values by filling them with the median values of numerical columns to maintain the consistencies in the data set. So with this step, we ensure that our data set is clean, structured, and ready for the further analysis. And then I will continue with the PCA. Okay, so for the PCA, first we ensure that only numerical columns are selected. And then dropping the irrelevant ones like monthly rent. We then standardize the features using standard scalar to normalize the data. And then next we apply the principal component analysis PCA, retaining 95% of the variance. Before that, we handle the missing values using the mean imputation to avoid the data loss. The PCA then reduce to the number of features while preserving as much information as possible. Then explain the variance ratio, confirm how variance each principal component retain. And then we convert the PCA back into the data frame. The data frame for easy handling. And then finally we split the data set into 80% training and 20% testing sets, ensure that both the feature and target variable are properly aligned. And then the printed shapes confirm the data splits. So this process helps to improve the model efficiency by reducing complexity while maintaining predictive power. Thank you.
Hello, my name is Michal, and let's now move to our model. So well, we have to import our libraries and then load a dataset, which is preprocessed dataset. Well, there is some data analysis and data description. There is distribution of monthly rent chart, correlation heat map, average rent by region. And let's now move on to data preprocessing, which is very important to ensure we won't have any errors. Well, let's now move to feature encoding and scaling. We use the cone transfer method. This is used to apply different transformations to different types of feature. This ensures that the dataset is properly formatted by training. So basically, it ensures proper preprocessing. We standardize numerical data and converts categorical variables into machine-readable format and prepares data for training and evaluation. Basically, next step is building the linear regression model. The pipeline objects ensures that all preprocessing and modeling steps are executed sequentially and in one unified workflow. The preprocessor, this applies the processing transformation defined earlier, scaling numerical features and encoding categorical features. Regressor, this applies the linear regression model to learn the relationship between input features and the target variable, which is monthly rent. And why we use pipeline, it's to ensures that data preprocessing is always applied before model training and avoids the data leak, ensuring that transformations are based only on training data and not test data, and makes workflow more efficient and readable. By running all this code, we find out that after evaluation, we have high MSE, which predicts that model has large errors and very low R-square score, which suggests that the model barely explains the variation in rent prices, meaning linear regression model well is basically not a good fit for our dataset. By this, we would like to explain that not every machine learning model is fit for basically any dataset. So basically, when we are trying to do some machine learning, we have to first think of suitable machine learning model. So that's all for our model, and now we can proceed to other section.
Good morning. This is my evaluation part where I evaluate the model with mean absolute error, mean squared error, and also R-square. The mean absolute error, the result is 385, which indicate that on average, the predicted rent is off by 385 ringgit, depending on the rent price. This error could represent a significant portion of the rental price. Then I also evaluate the root mean squared error. This RMSE penalize larger error more heavily and at a value of 469 ringgit, suggests that some prediction are off by a significant amount. This may indicate that the model is struggling with larger and more extreme deviations. Then after that, the R-square, the result is 0.144, which means that this is quite low. This means that the model can explain only 14.4% of the variance in rental prices. This suggesting that the model is not capturing much of the complexity in the rent price dynamic. That's all. Thank you.